Okay, cool. So, my name is Ethan Joseph, and my project is centered around the implementation and evaluation of feature extraction and logistic regression for accessible and computationally efficient cancer diagnosis. So, to begin, a bit of a background on cervical cancer. It's the fourth most common cancer in women and is the cause and was the cause of almost 340,000 deaths in 2020. And it's important to note that many of these deaths are in lower or middle income areas where the healthcare infrastructure is just not developed to the point at which these cases can be treated effectively. It's also important to note that cervical cancer can be completely treatable when found in early screening, and that's why screening is considered to be the most essential preventative measure for cervical cancer. And it generally takes years for it to develop from a precancerous or early cancerous stage into a potentially fatal stage. So the current screening methods, there's one main method, and then another, and they're often used in complements. So first is HPV testing. So this is just straight up testing of the HPV virus that has been known to be linked to cervical cancer. So this test requires extensive blood work to be conducted in a laboratory environment. So obviously, because a laboratory setting is required, it's often unavailable in lower income areas, and which is overall a pretty inaccessible test. And then the immune examination that's conducted by an oncologist is known as the POP examination or a POP smear. And this is when an oncologist or a doctor visually takes or samples cells from the cervix and then observes these cells under magnification to detect visual abnormalities. So, for example, an oncologist would literally take these cervical cells and search for, say, a malformed cell membrane or something of that sort. So, it requires an oncologist to manually review these samples. Thus, the processing time is upwards of multiple days, and once again, it does require an oncologist, which adds a layer of inaccessibility. So, about the biopsy images or pap smear images that I speak of, they're images of the cervical cells under magnification, so under a microscope, and these are collected through the pap smear. They're sampled from the cervix. Now, these cells are stained with various dyes to increase observability and thus make it easier to identify for an oncologist to identify any abnormalities. It's important to note that these images may contain mucus, dirt, or any other non-cellular material just because testing conditions are not always perfect. And as you can see in the bottom two figures, the bottom left figure is a non-cancerous sample, while the bottom right is a cancerous sample. You can see that the cells in the cancerous sample are somewhat larger and malformed compared to the non-cancerous cells. So this visual dependency that I speak of, meaning one could actually look at one of these biopsy samples and gauge whether they're cancerous cells or malformed cells. Because there's this visual dependence, AI has previously been implemented for such a classification task, and what's specifically used is a type of neural network known as a convolutional neural network. Now, this is effectively an AI model that processes images directly. So you feed it the original image pixels, and this model, through a variety of abstractions and layers, is able to transform, also known as convolving these images into features and abstractions that it can understand and process for future classification. So these models are very easy to implement and they're very effective. You can just toss an image at it basically, and you have a very high chance of it at least learning or to identify some features without much pre-processing or work on your part. But the drawbacks of this are that they're very resource intensive. These models have millions of parameters, millions of individual regression computations occurring simultaneously. Additionally, they may, through their transformation process of the image that is very much abstracted, they may misinterpret materials in the cell or dirt in the samples as cells, and this misinterpretation can decrease their overall classification accuracy. And just as a limitation to these models, overall, they typically only achieve up to a 90% classification accuracy, which is acceptable but is a drawback. And they also are lacking in transparency due to their immense complexity. These models, as I mentioned, have millions of layers, millions of underlying computations. So colleges can't really just follow along with what's happening in a convolutional neural network. It is very much just an abstracted binary, what does the network think, and not more of a supplemental to the oncologist itself. So I've actually conducted previous research in the convolutional neural network field. So I have done work regarding increasing accuracy, and my work was mainly centered around pre-processing the input images. So as you can see in the bottom figures, this is actually an algorithm that I developed that is able to isolate these cell masses before they're fed to a convolutional neural network. So it decreases any background noise and thus decreases the chance that a convolutional neural network will train on the quote wrong features. So I have done work on convolutional neural networks in the past, but at the end of the day, they're still very inefficient compared to, say, just normal machine learning or just a normal regression technique. So the overall objective of my project was to develop and train a computationally efficient and transparent model that uses logistic regression as opposed to a convolutional neural network to classify biopsy samples based on extracted cellular features as opposed to the entire image, while maintaining accuracy that meets or is higher than these conventional convolutional neural networks. So the way I did this effectively is through the development of an algorithm that is able to extract cellular features. So by cellular features, I'm referring to heuristic features that oncologists would typically identify. So things like the cell membrane area or the nuclei area, any malformations, any changes in the circularity or convexity of these cells, those actual visual features is what I was aiming to extract and then train a logistic model, so just a single regression computation upon classifying whether a sample is cancerous based on these features. And the reason I went in this direction is the algorithms and libraries to facilitate this are very, very computationally efficient and are widely implemented, especially in the library, the programming language library that I use to implement this. And logistic regression is very small, very efficient, and can run on a variety of hardware. So the data set that I utilized for this was obtained from memory data, and memory data is a pretty massive data set archive for various machine learning applications. This data set contained 962 declassified biopsy samples, meaning all patient data stripped, and they came in 3 variations of cervical cancer depending on severity. However, they were mainly composed of non-cancerous samples. This created an imbalance in the data set, so I eliminated all lower severity classes and basically equalized the cancerous and non-cancerous samples in the data set such that it was only trained upon high severity cervical cancer against negative samples. So this was done once again to decrease any bias and balance of the data set. Now, the feature extraction algorithm in question was developed in Python by the OpenCV library. It was composed of 3 main steps: to transform input images, isolate the individual cells, and then extract the aforementioned features such as cell area, perimeter, and circularity. So these input images were thresholded to isolate like masses of pixels. So this algorithm effectively iterated through each pixel of the image, tried to find like pixels, and then extracted them under the impression that they likely formed an individual cell. And then these isolated masses were evaluated for relevant features such as their area and perimeter. And then these extracted features for each biopsy image were averaged out and stored in the data set for future training. So this image in the bottom left actually shows the original image, and then to the right of that, the extracted image, and you can see the lines of basically representing the contours of the extracted cells. And then the bottom right figure basically shows the flowchart or process of this entire algorithm. So the logistic regression model itself was trained on these extracted features. It was comprised of only a single trainable unit and thus only a single regression computation, as opposed to the typically used convolutional neural networks, which execute millions of regression computations simultaneously. Um, and as typical with such a binary classification problem, it uses the sigmoid activation function and binary cross-entropy loss function, which allows it to make a binary classification. And it achieved, after training, a classification accuracy of 91%, which is actually higher than the typical, which is higher than what convolutional neural networks typically achieve, with their upper limit being around 90%. And it's important to note this model was trained in just a few minutes. It was executed entirely on computer, on consumer hardware. It was executed on my laptop, and thus only used the CPU for acceleration, no additional acceleration hardware. Now, I also
under 2 minutes, okay?
And I also developed a convolutional neural network to serve as a baseline. So this is one of the more typical techniques commonly used, and it was based on the VGD16 pre-trained network architecture to maximize its accuracy, and was trained directly upon the unprocessed biopsy images from the dataset and achieved an accuracy of 89%, which is typical and expected with such CNNs. It's important to note that this model during training required a non-consumer data center graphics card to accelerate computations, and this just really illustrates how inaccessible the training process for these CNNs are. So just to summarize our results, the logistic regression model achieved a higher accuracy than the typically used CNN while using significantly less resources and trained much faster than the CNN, which took almost upwards of 2 hours to train. And the graphs in the bottom left and top right illustrate the classification accuracy, but also the loss, which as it decreases is better because it increases because it depicts the model's increased confidence in its classification. Additionally, I developed a small microcontroller-based system to test the viability of both models, and it was observed that only the logistic regression model could run on such low-power devices. In the future, I hope to acquire additional training data, so the steps that I don't have to do data balancing and overall have a more generic data set for testing. And finally, I would like to do further research into the development of accessible portable testing devices. So with that, that concludes my presentation. Thank you very much.